This video is our second lesson for Unit 3 where we're looking at derivatives, and we're going to be looking at some more rules today that we can use to quickly find derivatives without having to do any limits. And we're going to start off with the product rule, which is what happens when you've got two chunks of algebra multiplied together. You can see the examples down below, and we're going to try to find the derivative of that. I actually do want to just very briefly here go back to last day's notes and just take a look at this rule here, the sum of the difference rule that said, hey, this was no big deal. Find the derivatives of the individual parts and then just either add or subtract them together, depending on what the question was, whether it was addition or subtraction. And you might think, oh, that's probably what's going to happen here. Well, I wish. It's not quite that nice. You can't just take the derivative of one chunk of algebra, the derivative of the other chunk, and then multiply them together. So just kind of highlighting that here, you can't take the derivative of that and then go and do the derivative of this, and then multiply those two things and hope to have the derivative of the product. And it just doesn't work that way. Here's what it does do, though. If you've got a u, that's a chunk of algebra, multiplied by a v, another chunk of algebra, and you're trying to find the derivative, then officially in a textbook you'll probably find this. The derivative is the derivative of u multiplied by the v just left alone, no derivative. But that's only half of it. Then you have to add the other way around. Leave the u, but multiply by the derivative of the v. Now when I keep writing the of x, it's very official. It's sometimes easier to just not write that and say, oh, okay, this is going to be u prime times v plus u times v prime. Right, we're going to alternate which one we do a derivative of. So this first example here, you can say, hey, this first part is the u, and then this binomial would actually be the v. And if I had to do a derivative of this, it is not going to be short. It's going to be pretty long. Okay, the derivative would be, okay, derivative of the u, that would be 12x squared. Then multiplied by the other part just left alone. Don't actually do any derivative here. So 3x to the fifth minus 8 x to the negative 2. And that's half of it. Then you have to go and do the other half. Plus, leave the u. And then the derivative of the next part. 15 x to the fourth. Oh, the negative 2 is going to hit the negative 8. We're going to have a plus 16 x to the negative 3 if we lower by 1. So these things get very long, and I don't want you to feel that you have to tidy them up right now. Okay, so don't feel there's a need to simplify and tidy it, even though the back of the textbook might do that. This next one, what's the derivative for this? Well, I can think of this as being my u, and that as being my v. So the derivative of 4, well, that's a constant. So the derivative of that would be 0 times the f of x just left alone, and then reverse. Leave the 4, and then multiply by the derivative of the v. I don't know what the algebra is there, so I'll just tell people, hey, you need to go and take a derivative of that, and then you'd have the answer. Now, when you're all done and you've crossed that off because it's 0, I just want to point out that this is exactly the same as our constant multiple rule. So I'm going to jump back a couple of pages. When we were doing this the other day, and we said, oh yeah, what if you've got constants in front of things? And we basically did the exact same question right here, right? And my point is it's consistent. So if it works, thinking about it as the constant multiple rule, or if you want to try to think of it as a product rule, you're going to get the same answer in the end. That's the neat thing about the calculus, which is also why I've got the next two examples looking identical. We're going to actually treat them two different ways. So for starters, I did say last day, whenever you can, it's good to simplify things. So what if we took this and said, hey, before we do the actual calculus, let's just go and, what's the phrase here, FOIL it all out, right? We could rewrite this and say, hey, the question is actually 2x cubed plus 4x squared minus a 6x minus a 12, if we write it kind of descending order. Then we could go and do a derivative and say, okay, what's the derivative of that? Well, going term by term, because it's all adding and subtracting now, this is quite nice. 6x squared plus 8x to the 1 minus just a 6 for that linear term. And the constant term, negative 12, the derivative is 0. So that's an answer. That's great. What if I wanted to think of this as a u multiplied by a v. Well, that works too. So the derivative would be the derivative of the u term. That would be 2 for the linear 2x, 0 for the 4, okay, just a 2, multiplied by the v left alone. Then add, that's how the product rule works, leave the 2x plus 4, and then do a derivative of x squared minus 3. Well, that would be 2x, and then the derivative of the negative 3 is 0. Now, I would normally just leave it like that, but it's interesting if you actually go and just tidy this up, which again, I would normally suggest is probably not worth your time, but if you do, you would have 2x squared minus a 6 plus, what are we going to have here, 4x squared plus 8x. And if we tidy that up a little bit more, we end up with 6x squared plus 8x minus 6. So my point is, as long as you're doing something that's fair mathematically, you can't get the wrong answer, right? Those are the exact same answer. Whether you said, oh, I'm going to simplify it first, or whether you said, no, I'm going to do the product rule on this thing, the calculus always comes back with something that's exactly the same. You just might have to do some simplifying in order to see that. Okay, this next one. Well, the product rule up at the top of the page only has 2 things, like a u and a v. It doesn't have 3 things. So here's where we're going to start to get creative. You start bundling stuff together, right? So what if we kind of think of this as being one thing just for a minute, and then we'll go and we'll do our derivative. So my derivative for this, it's going to get really long, so back way up to the left here. Let's do a derivative of the first thing, that's 7x squared minus 8x. Here, I'll use some color to help you out. That would be 14x minus 8. There, I did do a derivative there. But don't do a derivative on this next part. Just leave it alone. So you'd have 2x plus 1 times 4x squared plus 5. There, we're halfway through the product rule. Now we reverse roles. We'll say plus, because that's how the product rule goes. We'll leave the 7x squared minus 8x. Okay, yeah, just left it the way it was. And now I'm going to go and do a derivative. I'm going to put it right here. I'm going to use some brackets, and you're going to see why in a minute. They actually have to be there. Okay, in those orange brackets, I'm going to put the derivative of that highlighted blue material. Oh, well, that highlighted blue material is a product. So I have to go and do the product rule. So I would go and do the derivative of the first thing, and that would be a 2. Leave the other part alone, just don't touch it. 4x squared plus 5. Now reverse. Leave the 2x plus 1 alone, and then do a derivative of the 4x squared plus 5, which would be 8x. Now I do have to have those big orange brackets in there. They don't have to be orange and they don't have to be square, but they have to be in there in order to get the order of operations right, have the right feeling. Do not take the time to tidy this up right now. It's not worth it. All you need is to have something that you could evaluate for x to find the slope of y at any given point that you want. Okay, the next one. Whoa, geez, we've gone from 3 things to 4 things, right? So 4 different things here. There's this 8, and then there's this f of x, and then there's this g of x. Geez, I've run out of highlighter colors. And then there's this thing, right? 4 things all multiplied together. So what I might want to do is kind of break it up in my mind and say, well, for a moment, why don't that be called u, and that could be called v. Here it goes. I'm going to do a derivative, and it's going to get really long. But at least I don't have to do a limit. Okay, so the derivative of u. Oh, well, that's that yellow thing hitting the blue thing. That's a product rule. So for a few seconds, I'm going to exercise the product rule. And I'm going to do my derivative. So I would say, okay, the derivative here would be the derivative of 8 multiplied by f of x. Okay, so that's 0 multiplied by f of x. Well, that's nothing. And then plus, leave the 8 multiplied by the derivative of f. Well, I don't know what f is, so I'll just tell people, hey, you need to do a derivative. By the way, I could have saved myself a little bit of time if I had gone and done that as a constant product rule, but whatever. There we go. I have gone and found the derivative of u, and now I'm going to multiply it by v, just left alone. Just don't even touch it. Just write down the whole thing. Two things multiplied together. Okay, halfway, plus, leave the u, so just leave this 8 times f of x, don't want to touch it, times, and now here comes the derivative of v. Now the derivative of v is going to have a couple of things that are added together, and I want it all to hit this 8 times f of x, so I absolutely must have some brackets in here in order to get this to work. Okay, derivative of v. Well, I would do a derivative of that pink stuff, so that's going to be g prime multiplied by that yellow stuff just left alone, 3 x squared minus 2x, oh, this is going to get tight, and then add, leave the g, multiplied by the derivative of that last part. That's going to be 6x minus 2, and that's going to be all the room that I've got in here as well. Just breaking it down bit by bit, layer by layer. It's like peeling it off like an onion, trying to slowly get to the very center of this thing. So that's how you do the product rule, including triple products and quadruple products. Now let's look at the rule for division. And if the rule for multiplication was a bit ugly, well, this is really ugly. When you've got some algebra divided by some algebra, the way that you can find the derivative without using limits looks like this. It's also a fraction, and in the numerator, it's going to go as the derivative of the top multiplied by the bottom, and then subtract, leave the top, multiplied by the derivative of the bottom. And you might think, oh yeah, that would probably be it. That would look like the product rule, but with a minus. Yeah, but there's even one more part. You have to divide that whole thing by the bottom chunk of algebra squared. Let's try that out. Okay, oh, by the way, another little short way of writing that. You know, if you're ever sitting there saying, oh, is there a shortcut for writing that down? Yeah, this could be written this way, if you chose. Just an option. Okay, very first question. This is actually a quotient. It's not a product, right? That -1 means that this question is really trying to say this. 5 x squared plus 11 in the top, all divided by 3 x to the -2 plus x. Okay, the derivative. You know, I always write down y prime. I should give good old Leibniz a little bit of time here. How about dy dx, the derivative? Okay, for a quotient, you get a quotient. So I need to write down a nice big fraction here. It's going to get big. Here we go. Derivative of the top, that goes first, times the bottom, left alone. Just leave it as it is. Then a subtract, because we're doing the quotient rule. Leave the top, and then the derivative of the bottom. Just going to do some power rules here. Looks like I'll have a -6 x to the -3 plus a 1. All sitting on top of that bottom, that denominator squared. Don't try to tidy it up. You know, it's actually a complex fraction with that x to the -2 and the x to the -3. Oh, just leave it. It's fine. We're not going to use it enough to justify cleaning this thing up. Okay, this one. What are we going to do here? Well, we can rethink this question using exponents. This root x, that is the same thing as x to the 1/2. The cube root of x is x to the 1/3, but it gets multiplied by this x to the 1. So that stuff there, not worrying about the 6, that's actually x to the 4/3. It might be easier if I think about it that way. Now here goes the derivative. y prime. We'll go with apostrophes, we'll make Newton happy. It is going to be a big fractional answer. It's going to be pretty long. Here we go. Derivative of the top. Okay, going term by term. 8 x to the 1. Then this one, this minus x to the half. Well, the half comes down, so minus a half x to the lower by 1. There, that's just the derivative of the top, based on last day's rules. Multiply that by the denominator left alone. Okay, we're getting there. Now, subtract, because it's a quotient. Leave the top, so we'll go 4x squared minus x to the 1/2. And now the derivative of the bottom. Well, a couple of terms in there, but for sums and differences, you can go term by term. They're a lot nicer than products and quotients. So we'll have a 15 x to the 4th minus, okay, that 4/3 is going to come down and hit the 6. All right, so when it does that, we're going to have 24 divided by 3, that's going to be an 8. And then lower the exponent by 1, x to the 1/3. All sitting on top of the bottom squared. Now, I'm not actually going to FOIL that bottom all out, be there all day, but I'm at least going to tell people that that's what I would do. That would tell you the derivative. That would tell you the exact slope of the tangent line at any point you wanted to check. Okay, this next one, this will barely fit in this space that's here. Back way up here, y prime. Here we go. Big picture, when I first look at this, I'm seeing a quotient. I'm seeing a fraction. But then inside the fractions, both in the numerator and in the denominator, I'm seeing some products and some additions and subtractions. I'm seeing lots of different things in there. So let's go slow. First thing I need to do is I have to write down the derivative of the top. Right? My rhythm is going to be derivative of the top times the bottom minus the top times the derivative of the bottom. Okay, first thing, derivative of the top. Here we go. So, derivative of the top. Oh, that's going to be a product rule. So I'm going to have, as I do my product rule, the derivative of 5x plus 2. Well, the derivative of that linear term is just a 5, and the derivative of 2 is 0. Okay, there, I did the derivative of that one. But now I have to multiply that by the 7x minus 8, just left alone. That's a product, so I put a plus in here. Going to leave the 5x plus 2. And then multiply that by the derivative of the second part here. Well, that would be a 7. There, all of that is just the derivative of the top. I'm going to get my order of operations wrong if I don't drop in some brackets here. So there we go. Derivative of the top. Now, times that by the bottom. So I'm going to multiply that by g of x plus 8x. But if I just leave it like that, it doesn't say what I want. It doesn't say the big green bracketed thing hits the g of x plus 8. Right now it's only hitting the g of x. So again, I might need some brackets to get the theme right. And so right now I've got this top derivative times the bottom. But I got more to do. I got to go and do this. Right? There's more to do for this top of this fraction. Subtract because it's a quotient. Leave the top. Just don't touch it. Leave it like it is. And now we're going to write down the derivative of the bottom. Okay, well, I don't know who g is, so I would just tell people, like, look, you got to do its derivative. Okay, well, that would just be denoted as g prime. And then the derivative of 8x, that linear term, it's like a graph. Y equals 8x. Its slope would be just 8, so plus 8. But if I just leave it like that, it doesn't say what I want. It's all got to bump into this blue stuff that's there. So I might want to throw on some brackets there so it says what I want it to say. And then all of that gets divided by the denominator squared. Now, we're probably, when we do things like this, only going to need this for a few seconds. You might need to figure out, hey, what is the slope? What is the value for the derivative at x is equal to 11? And you would put one value for x in. And if that's all you're ever going to use it for, then let's not waste our time and try to simplify that. Let's just leave it as it sits. So that's the quotient rule, and that one's pretty darn ugly. Let's move on and try this one, the reciprocal rule. I should tell you, just my own little editorial about this thing here. Yeah, sure, I'll show you the reciprocal rule, but you don't really need this. You can think your way around it. I'm going to show you that in example 4 at the bottom of the page. But if you do have a fraction that's a nice 1 in the top and then some algebra on the bottom, that's what this is trying to say. And then you're trying to do the derivative, right? Put that little apostrophe on it. Or here's Leibniz saying, let's do the derivative of 1 over some algebra. Well, if you think about what's going to happen, you would have the derivative of the top, which is 0, times the bottom left alone. Well, that's not going anywhere fast. Subtract, leave the top, and then derivative of the bottom all over the bottom squared. Okay, well, we can tidy this up because that first part is just nothing. And I don't know if this is worth it or not, but people actually say, hey, look, here's an official rule. The derivative is the negative sign, the derivative of that algebra that was in your fraction down in the denominator, all divided by that same algebra squared. Okay. Let's try it following the rules for example 3, and then in example 4 I'll show you how you can work around it. But example 3, it says please go and find the derivative, and then maybe when you're done, can you go and check it out at 3 for that function? Yeah, okay, so it's a reciprocal, right? It's 1 over some algebra. This algebra right here is what up in the rule we would have called f of x. Right? So slightly different f's. Here this f is the stuff on the bottom, and here this f is the whole thing, 1 over it. But I'm going to exercise this plan and see what we come up with. Okay, my derivative would be, I'll follow the rules. So it's minus the derivative of what you found in the bottom. Well, there's the stuff on the bottom. So minus the derivative of that. Well, that would be 6x squared minus a 3. So yeah, I've got the opposite of that, all sitting on top of that algebra that's in the bottom squared. Okay, that's done. Now, they're saying, well, that's nice, but can you use this one time, right? Like I was saying before, often we only use these once, and we're going to use it once when x happens to be 3. So you'd say, oh yeah, sure. Not a lot of point simplifying the algebra if you're just going to use this one time with x being 3. Now you would substitute stuff in. It's okay, negative, got a 6 times 3 squared minus a 3. I'm just evaluating this blue stuff, putting 3 in for x. And then 2 times 3 cubed, lots of 3's here, minus 3 times 3, all squared. And if I'm not mistaken, I think this to 4 decimal places, which is our rhythm, our rule for CalCP. It's negative decimal 0.251. We can stop there. Okay, so yeah, there's the quotient rule, right? It says if you've got 1 over some algebra, yeah, 1 over some algebra, just follow this plan. But watch this. I want to show you how you can get this question right 3 different ways, and they all work out to be exactly the same thing. So the function might be 1 over x to the 4th. So here's one option. You could use the power rule. That's probably our favorite, right? It's so nice and easy. And you could say, hey, thank you for showing me that function, but if it's okay with you, I would like to rewrite it in a way that looks nicer. That is the same thing as x to the negative 4. And so then you go and you do your derivative, and you say, yep, here we go. Derivative would be negative 4 x to the negative 5, which if you wanted to, you could rewrite like this. Negative 4 sitting on top of x to the 5. Done. Don't need the quotient rule. Or you might say, no, I like following the rules. I learned this rule about the quotient rule. Okay, fine. Or sorry, I didn't need the reciprocal rule. Here we go using the quotient rule. You could say, okay, let's look at that thing as a fraction. The derivative would be derivative of the top, Well, the derivative of 1 right there would be 0. So 0 times the bottom, left alone, minus, leave the top, derivative of the bottom, all sitting on top of the bottom of your fraction squared. Ooh, well, that's a little messy. What do we have here? We got negative 4 x cubed all sitting on top of x to the 8th. Oh, hey, that tidies up too. You guessed it, negative 4 on top of x to the 5th. Same thing, right? Or here it comes. You're a rule follower, and you're like, hey, I learned this rule called the reciprocal rule. Okay, great. Let's use the reciprocal rule. And you'd say, all right, here's my answer. If you see some algebra down in the bottom, and I do, right? I see this x to the 4th down in the bottom right here. Right? Let's follow the plan. So then the derivative would be the negative multiplied by the derivative of that algebra down in the bottom, all sitting over that algebra squared. Yeah, well, guess what? We're right back here again. So do you really need the reciprocal rule? No, not really. You can either get at it as a quotient rule, it just takes an extra step, or you can think about it maybe sometimes as even being a power. All right, just a couple more pages here. The second to last page is a set of exercises, and you'll see these all over calculus textbooks and on a lot of calculus exams as well. And it's probably important to know, why do students have to do these questions? Why do teachers like to throw them at them? And the answer is, you can't really do them on your normal graphing calculator. So it's a way for us to check and see that you know the rules without letting you just say, oh, no problem, I'll put the function into my calculator and just ask it to do the derivative value. So instead you have to know the patterns. So it says here, suppose u and v are functions of x, so they're made up of x's. And they're beautifully differentiable at x is equal to 2, so nothing ever goes wrong at 2. And then they're going to give us a few bits of information, like for the function u, here's the y value and the derivative at 2. And the same for v, we have a y value and a derivative at 2. And they're saying, can you find the values for these chunks of algebra at 2, right? So this first one is just a product. What happens if u and v are multiplied together? And you might be wondering, well, what's u and what's v? What do they look like? And it's like, no, not going to tell you, right? You're on a need-to-know basis, and nobody's going to tell you what u or v actually looks like. So you'd have to tell them, well, it's a product, so you should do the derivative of that first thing, multiply it by the other one left alone, and then switch roles, leave the first one, and do the derivative of the other one. Oh, and then when you're done, go and evaluate at x is equal to 2. Okay, well, I can do that now, right? I can see these numbers like all up here. I can go and embed them in here, and then I can say, oh, okay, well, it looks like u prime at 2 is a negative 4. Sorry. Negative 4 multiplied by v, figured out at 2, that's a 1. Plus, leave the u, figured out at 2, that's a 3. And then v prime, figured out at 2, that's a 2. Okay, so negative 4 plus 6, 2. 2 is my answer. Okay, now let's just back up and look at this thing here for a second. If instead of saying to evaluate this at x is equal to negative 2, if they had said, oh, can you do it at x is equal to 9? The answer is no, because you only gave me info up here about what happens at 2. So we can only do this for these very these very specific questions that are set up for this. Again, teachers like to do this because they can quickly check to see that you know the product rule, and I know if you've got an answer of 2, yeah, you've probably got it right. So they can, mark the test really quickly. Same plan for this one. I could say, hey, please go find this derivative, and I know that for you to get it right, you're going to have to know the pattern for a fraction goes like this, that it's going to be u prime times v minus u times v prime, all sitting on top of v squared. And then again, we're going to go and figure this out at the 1x value where this is possible for us. So we would have negative 4 times a 1, subtract a 3 times a 2, all sitting on top of a 1 squared. Okay, well that works out to be negative 10. And just by quickly looking at your test paper, if I see the negative 10, I'm pretty sure you're going to have that one right the correct way, right? A little more checking, I can see that you've got it for sure. Okay, so what are teachers doing when they throw this at you? Oh, do you know the constant multiple rule? Do you know the sum and difference rule? Basically, can you look at that and say, oh yeah, the derivative would be like this. Leave the 3, u prime. Moving down the road with a subtraction, leave the 2, v prime. And then minus 2 times, got a little product here, so maybe I'll just put this in some brackets. U prime v plus u v prime. And if you would have said, hey, could I not have put the 2 and the u together, maybe even the minus sign? The answer is sure. Yeah, just pick away and then stick to it and you'll be fine. And then you would go and say, oh yeah, now I need to go and evaluate this when x is equal to 2. And you can try it out. One of the things you're going to find is you're going to get negative 20, right? So I can quickly look and go, yeah, you got negative 20. I probably know for sure that you know how to do the sum and difference rule. Oh, here's the reciprocal rule. And again, you don't need to know it. You can say, can't I think of it as a quotient? Derivative of the top is, 0 times the bottom left alone minus, leave the top, derivative of the bottom, all over the bottom squared. If you know the reciprocal rule, all that does is let you skip this one little step in there, right? Because it's going to be 0 anyways. And then you'd say, oh yeah, let me go and evaluate this at x is equal to 2. And then I can look at your work, and if I see that you've got 4/9, then I'm like, yeah, okay, yeah, you know those rules. Let's try this one out. Okay, it looks like a quotient to me, right? So yeah, I'm being tested to see whether I know the quotient rule. Derivative of the top, no, that's a sum and difference. I'm going to do them separately. So I would have 3 v prime, and then derivative of 2 is 0. Oh, okay, done. So there's the derivative of the top, times the bottom, for u, I'll just put the brackets on for emphasis, minus, leave the top, 3v plus 2 times the derivative of the bottom. Oh, constant multiple rule. 4 is going to hang around. U prime, all sitting on top of the bottom algebra squared. So 4u gets squared. And then you would go and say, all right, let's go and see what you get when you have x is equal to 2. And you'd put the values in based on what you see at the top of the page. You'd come up with some numerical value, and then I could check it and go, yeah, you got the same numerical value I did, you're fine. I don't even know what the answer is, to be honest. I don't even care. Okay, maybe we should just go and put the numbers in, and then we'll leave it at that, right? You can say, okay, well, this would be 3 times, and then looking back, the v prime at 2 is a 2, multiplied by a 4, multiplied by u when x is equal to 2, and that's a 3. Subtract 3 times the v when x is equal to 2, that's a 1, plus 2, that's all in a bracket, and then 4 times u prime, figured out at 2, which is a negative 4. All sitting on the bottom. And so this is really just so that your exam marker can quickly check and see whether you're probably on the right track or not. Down in the bottom, 4 times the value for u when x is equal to 2, which is a 3, and that gets squared. Whatever that works out to, I don't even know what it is. Instead of worrying about that, let's move on to the next page. Multivariables. This is where the Leibniz notation works really, really well. So this might be some physics story. I know in physics class you might have a d in there for VIT plus 1f AT squared, but we've got d's in our calculus. So for calculus stories, we very, very often use s to stand for the position of the object, kind of like the displacement if you wish. And this question says, can you go and find the derivative of that function s? And then the key thing is, dt. So it's saying, okay, t is the main variable of the day, right? So where you see that, that's the thing that we're actually doing the algebra with respect to. And if it's not a t, then it's a constant. So in this story, this initial velocity from physics, that is some sort of constant number. It might be a 5, it could be a negative 11, but it's just a constant. The same thing with this a, just a constant. It's not anything that we have to do a derivative of. We only have to do a derivative with respect to the variable t. And so these go actually very fast. We've done this page in no time. The derivative of position with respect to time, okay, this is otherwise known as velocity. All right, when I see this VIT, this is no more complicated than a story that kind of looks like this. Maybe like 3x, right? Some constant times that independent variable, and then plus 1/2, I'll pick an a value, maybe like 9.8, some constant, and then x squared. That's all we're doing, right? It's just that who knows what the a is? Is it 9.8? Maybe it's not. Maybe we're on the moon. Initial velocity, is it 3? I don't know. It's some number. And if I did the derivative of 3x, I would just say, wow, the derivative of that linear term is just 3. Well, same idea, but here it's just going to be a vi. So that's the constant out front. That'll be my derivative. And then moving down the road, this 2 would come down and actually bump into this number. It would actually eliminate the half, right? So the 2 comes down, hits the half, and I would just have, instead of half a, I would just have a, and then t to the 1. Just leave it like that. That's actually like the physics formula that says Vf is equal to Vi plus At. Okay, the next one, got some formula that relates a whole bunch of things together. Maybe this is something from chemistry, and they've said, oh, can you go and do a derivative? Oh, by the way, capital T is the main variable of the day, right? That's the only thing that's changing. Anything else, like the 2/5, the n, the 3, the a, those are all constants. Okay, you just have to think about what's actually a variable and what's actually a constant. So if I was doing this derivative of whatever that is, maybe pressure with respect to, who knows, temperature. Okay, well, I'm seeing just a constant multiplied by some interesting stuff, and one of the things I know from my constant multiple rule is that constants just hang around. So the a won't go anywhere. It's not a variable, it's just a number, but I don't know what the number is. So it hangs around, and then I bump into this big bracket. Okay, working term by term. Derivative of 2/5 t, that's a nice little linear term. The derivative would just be 2/5. Moving on down the road, subtract. Oh, a quotient. Okay, here we go. Derivative of the top. Now it's not a 1, it's actually a 0, because n isn't a variable, it's just a constant. It's not the variable capital T. So that's just a 0. And then leave the bottom alone. Subtract, leave the top, and then the derivative of the bottom. Well, that would just be a 3. And I still haven't finished this fraction yet. All divided by the bottom squared. There. It's a big ugly mess, but it's done. It's exactly what the derivative with respect to capital T would be. This one, trying to do a derivative, again, of position. Looks like a physics story. And then when they're done, they're saying, oh, can you go and figure this out at the moment when time happens to be 4? Oh, by the way, we'll tell you later now that the initial velocity was 15 and the acceleration was negative 9.8. So the first thing I have to do is this. I have to go and do that derivative. Then I'm going to go, after that's done, and do this evaluation at that time with the guidance of what the constants are. So when I first just do the derivative, ds dt, and that was known as velocity, that would be, based on the upper example, vi plus at. Great. Now, let's go and do this evaluation. What is that worth at the moment, at that one little moment in time, when time happens to be 4? Oh, and by the way, here's a little bit more information. Here's some numbers that have not been changing all day. The initial velocity, that constant, is a 15. Oh, and the acceleration is negative 9.8. Oh, okay. Well, this would be pretty easy to figure out. So this would just be the VI, 15, plus negative 9.8, and then we're doing that very specific time value of 4. Okay, great. I think the answer ends up being negative 24.2. I'm going to check it right now, actually. I just want to show you that on your graphing calculator, you can actually ask it to do this, right? So I'm going to, first of all, lock in some constants. So I'm going to use the memory in my calculator and say, hey, 15, I'm going to go and store you into V, just so that you can remember that. And negative 9.8, I'm going to go and store you into A. So those are constants, those are locked in. And now I'm going to ask my calculator, hey, can you go and do this derivative? And then can you figure it out at 4? And my calculator is not very smart. It can only do this numerically by just like wiggling the numbers a bit, but it'll try. I'm going to hit the math menu. And so I can say, yeah, derivative please, which is number 8. Now I've just got the older TI-83, so it's a bit messy looking. I'll show you what you would type in on the TI-84 here in a second. But I'm going to basically type in that algebra. So I'm going to say, oh yeah, it's V, if I can find my V, plus AT. That's my, oops, sorry, I'm looking at the wrong one. It should be up here. Try that again. VT, my apologies, plus 0.5 times A times T squared. There's my function. And then I have to tell it after a comma, hey, what is the actual variable that we're doing the derivative with respect to? That's going to be this t right here, right, where Leibniz says dt. So I'm like saying, oh yeah, hey, by the way, t's are changing. And it's like, okay. And then after that, I'm going to put in the value for t that I wanted to check at. I'm like, oh, please check it at 4. And then it goes and says, okay, there's the answer, negative 24.2. Now, if you have a TI-84, slightly nicer notation, right? It's going to say D, and then D, and then there's a box, and then a big box here, and then there's going to be like an X equals, and then another box. So what you would go and do is you would say, okay, I'm going to do this VT plus 1/2 A t squared, and then here you could put in a t that'll instantly change, I believe, this to a t, and then you can then put in, figure it out at 4, and it'll say, okay, I get it, we're doing a derivative with respect to t. So just a couple of different ways to get that to work. Key thing is realizing which of those letters are constants and are not changing. They're just behaving like numbers, and then which ones are actually changing. And that wraps up our second lesson.